This is the homework help video for chemistry, homework 3.2, or unit 3, homework number 2. There's 6 questions here. I will do 1, 2, and 5. I'll do 1, 2, and 5. On number 1, we've got atomic radius, and the first thing we're supposed to do is define that. For atomic radius, to define this, it's really not too bad. It's just a gauge of the atom size. So the best thing to put here is half the distance between the two nuclei, or the two nucleuses, of two adjacent atoms. If we were going to draw that in two adjacent atoms, we would have a nucleus with the electron cloud. Then we have another electron cloud, and we're probably going to overlap a little bit. And we're going to have another nucleus, and we're going to be looking at this distance right here. Sorry, that was kind of a bad little squiggly thing. I'll try to draw a better one. There you go. We're going to be looking at that distance right there, and that would be the atomic radius. And the other thing that it measures is the distance across this atom. So that's atomic radii. The next thing it asks us to do is what is the trend as you move from left to right, and I'm going to draw a really rough periodic table here. Look something like this. Drop down in the middle. Something like that for the periodic table. As you move left to right, atomic radius is actually going to decrease. So as you move this direction on the periodic table, the atomic radius will decrease. And that seems backwards, but if you think back to the shielding effect that we talked about in class, that's the reason for that. We've got more electrons in there. Excuse me. We've got more electrons in there, and we've actually got a greater attraction when there's fewer electrons of interest, or fewer valence electrons. We get more attraction there. When we add the extra electrons, we cancel out some of that positive charge, and our atomic radius is a little bit smaller. As we go from top to bottom, it's a little bit more predictable. As we go down, the atomic radius increases. Sorry about that. So that should be number 1, ranking the following elements by increasing atomic radius. We've got carbon, aluminum, oxygen, and potassium. The smallest one of those is going to be the one that's closest to the top and furthest to the right. So oxygen would be number 1. The next one would be carbon. And then we would go to aluminum and then potassium, because we're just kind of moving down and to the left there as we get larger. So that's ranking those elements in order of increasing size. This is small, and this is large. And then drawing the trend, we just did that. It's sitting there on that periodic table. Okay, we'll go ahead and do the next one now, and I'm just going to erase and do the same, use the same periodic table here. So we'll get this stuff erased. And for this one, we're looking at the ionization energy. Defining ionization energy is a little bit tricky sometimes. The ionization energy is the energy that it takes to take an electron from a neutral atom of that element. So it's how much energy, or the energy required, to remove an electron from the neutral atom. To remove an electron, electron, that's the notation for electron, remember, from a neutral atom. The trend as you move from left to right, the ionization energy increases. the further right we go, the more they want to hold on to those electrons. Nonmetals really don't want to get rid of their electrons. They hate that. Excuse me. As we move down the periodic table, this actually gets easier. So the the ionization energy decreases. Because these elements down here have more electrons, they're more willing to give them away. These elements up here, they don't have very many, and they're very attracted to them, so they want to keep them a lot. So the most the ones with the highest ionization energy are up in this area right here of the periodic table. The following elements by increasing ionization energy, we've got sulfur, oxygen, neon, and aluminum. Neon is going to be number one. It really doesn't want to get rid of an electron. So, that's going to be the last one. Neon has the highest. Aluminum is the most willing to give one up that we have on that table. Aluminum is the most willing to give one up. Next on our list here would be sulfur, and then oxygen, and then neon. Neon absolutely does not want to give an electron away. So that should be number 2 for you. Number 5 now, what is the difference between electron affinity and ionization energy? If you look back in your notes, electron affinity is defined as the energy given off when a neutral atom in the gas phase gains an extra electron. So electron affinity is energy given off when an electron is gained. The ionization energy, on the other hand, ionization energy is the energy required to take and remove an electron. So the key words here really are required and given off. So in electron affinity, we're giving off energy. In ionization energy, we're requiring or bringing in energy. And then also this remove and gain. So those are the big differences there between electron affinity and ionization energy. I hope this helps a little bit, and I will see you soon.